Again, welcome to Mathematical Structure for Computer Science, CS 113. In these lectures, we're going to continue with our probability chapter. Here we are going to talk about probability theories. So our main objective is how to assign probabilities, also probabilities of complement and union of events, conditional probability, independency, Bernoulli Trials, and the binomial distribution. Also, we're going to discuss about random variables, and we have an example for a birthday problems, and also the Monte Carlo algorithms. So assigning probabilities, as we saw in the Laplace definition from the previous sections, here we say assuming that all outcomes are equally likely. So in Laplace definitions, in our, again, the first section of probability lectures, we always assume that all the outcomes are equal. So for example, if we are doing an experiment to toss a coin, the possible outcome is 2. So it's equally, the head is 0.5 and the tail is 0.5. Now we are going to introduce more general definition of probabilities that will avoid this restriction. Again, let S be the sample space. Again, our previous lectures, we said the sample space is all the possible outcome of an experiment or all possible events outcome in an experiment. So here we say let S be a sample space of an experiment with a finite number of outcomes. So here we assign probability P at S to each outcome S, so that, again, our first theory in probability values is always between 0 to 1. If it's 0, we are 100% sure the event will not happen. If it's 1, we are 100% sure it will happen. Otherwise, between 0 to 1. Now, tossing the coin, we only have a 2 possible outcome. So the probability was half and half. Throw a dice, we may have 6 possible outcomes. Either we have 1, 2, 3, up to 6. So the probability of having 2 will be 1/6. That's using the Laplace definition. So again, we select S be a sample space of an experiment with a finite number of outcomes. Here we are going to assign the probability P at S to each outcome, so that probability at S or P at S will be either equal or greater than 0 and less than or equal to 1. So the sum of all the probabilities will be 1. This is one of our first theory in probabilities. Tossing a coin again, the possible total outcome is 2. The sum of those 2 outcomes, which is head and tail, is equal to 1. That's the probability of both head and tail sum is 1. So the function P from the set of all outcomes of a sample space S, we use the term probability distribution. So the function P from the set of all the outcomes of the sample space S is called the probability distribution. Now we have example here assigning probabilities. Here they say, what is the probabilities should we assign to outcome H for the heads, T for the tails, when there's a fair coin is flipped? Now the keyword is fair. So that means the probability of these 2 events will be equal. Now here is tossing a coin. The possible outcome is only 2, either probability of H or probability of T. So this means it will be half and half, and the sum will be 1. So here we say what probability should be assigned to this outcome when the coin is biased, so that the heads come twice as often as tails. Now we have a different condition. So we can see the first condition first. The fair coin means probability of H is same as probability of T, because we have the same, only 2 outcomes, H or T. So it's half. The sum is 1. Now there's a condition here. Now the head and tails outcome are not fair. we said that what probability should be assigned to this outcome when the coins bias, so that heads come up twice as often as tails, which means if I toss the coin 3 times, head will be 2, tail will be 1. So this means for biased coins, we are going to have a P at H equal to 2 times P at T. Because if probability comes once, H will come twice. So P at H should be 2 times P at T. Now, because both of them, P at H plus P at T is 1, we can write the expression as 2P at T, because P at H now is 2P at T. Because P at H comes twice than P at T. So P at H will be 2 times P at T plus P at T. So here we add the 2 together, we get 3P at T equal to 1. Now to find P at T, we get 1/3. So if 1/3 is P at T, then P at H will be 1 minus 1/3, which will give us 2/3. So again, we set up this condition based on the condition of the question. The question said, the first part, probability of head, probability of tail, tossing the coin is a fair. So which means both will be equal. So it's half each, so it's 1. Second condition said, when probability at T appear once, P at H will appear twice. So which means P at H equal to 2 times P at T. So we find P at T first, which will be 1/3. Then 1 minus 1/3 will give us P at H. So next we go to uniform distribution. So first we start with the definition. What is a uniform distribution? Here we say, suppose that S is a set with n elements. The uniform distribution assigns the probability 1 by n to each element of S. We should know that we could have used Laplace definition here. So example again, consider again the quite frequent example, but with a fair coin. So with a fair coin, the uniform distribution will be P at H is half, P at T is also half. Next is the probability of an event. So the probability of an event E is the sum of the probabilities of the outcomes in E. So here the symbol represents P at E equal to the sum of P at S. Note that here now no assumption is being made about the distribution. We don't have any assumption, whether it's a fair coin or it's a fair toss of a coin or fair throw of a dice, no any assumption. The reason why we may have maybe 3 different events and maybe or outcomes, and maybe their probability will be different. So let's see an example here. Suppose that a die is biased. So now the die, if a die is fair, we know a die consists of 6 different parts. So probability of getting any part will be 1/6 if it's fair. Now we say the die is biased, so that 3 appears twice as often as each other numbers. So 3 can appear double than all the rest of the numbers, but that the other 5 outcomes are equally likely. So this is a good one. We have numbers from 1 to 6. All of them appear equally. They are fair, but 3 comes twice before all those numbers. Now the question says, what is the probability that an odd number appears when we roll this die? Now remember, 3 is an odd number also. So now we can say, okay, our event, we have only 3 odd numbers, which is 1, 3, 5. So we are looking for a probability that 1, 3, 5 will appear. Now, if the die is fair, the probability that we may have a odd number is 135 will be half, because we have 3 even numbers, 3 odd numbers, so it will be half. But here, because of probability of 3, so here we say we have probability of 3 equal to 2 by 7, to be 2 by 7. Why? Because 3 appear twice among all the values. And P at 1 equal to P at 2 equal to P at 3. If all of them are the same, so it will be 1/7. Previously, we said P at 3 is 1/6, because if each appear at the same time, it's 1/6. But because P at 3 appear twice, now we have 7. We have 1 to 5, 3 included will be 6, but 6 is twice, so 7. And since 3 appear twice, that's why we have 2 by 7. So if we have 2 by 7, the rest appear equally. So from 1, 2, 4, 5, 6, excluding 3, it will be 1/7. Now, if we have these two values, we should get 1. So our answer is we want any of these 3 odd values to appear. So the probability of 1 plus probability of 3 plus probability of 5 will be 1/7. Probability of 3 is 2/7. Probability of 5 is 1/7. So when we add, we get 4 by 7. So again, the keyword is, what is the probability that an odd number appears when we wrote this down? If it's fair, then everything is 1/6 throughout. So it will be 1/6 plus 1/6 plus 1/6 and 3 times, which will be half. But here they told us 3 appear twice as often. So which means the total that I will throw will be 7, because 3 is twice. And 3 we get 2, so we get to 7. So next we move to the probability of complements and union of events. So probability of a complement of an event means 1 minus the probability of the event. This means we know the total probability sum is 1. So if I have a probability of A is equal to, let's say, 4.4. Probability of A equal to 0.4. Probability of a complement of A or not A will be 1 minus 0.4. So complement means not. So probability of not E or complement of E will be 1 minus probability of E. And since we know that the sum of all the probabilities outcome is 1, we know that probability of E plus probability of complement E will give us 1. Now, union means either E1 or E2. So probability that E1 or E2 will appear, it will be probability of E1 plus probability of E2, but sometimes we may have both appear at the same time. So minus that section, which will be probability of E1 intersect E2. Now, probability of E1 intersect E2 means the probability that both events occur at the same time. The union means either the first one or the second one, or both. But probability of E1 plus probability of E2 means all the possible probability of E1 and all the possible probability of E2, and also all the possible probability of U1 and E2 together. So here we have to subtract that section out. So we subtract the probability of U1 and U2 together, which we use the term intersection. So the union is like a U symbol. So combination of events. Here we say that if E1 and E2 is a sequence of pairwise disjoint events in a sample space S, then probability of EI, we start from I, will be the sum of all the probability of E. I can be any amount of numbers. Let's say we have 3 events, then the sum of all the probability of the 3 events. Now, next we are moving to conditional probability. Conditional probability means we have some condition before something may happen. So let's say, for example, what is the probability that if I smoke a cigarette, I will get cancer? I will get a lung cancer. My condition is smoking cigarette, and my outcome is lung cancer. So here we say probability of E given F. We read this as probability of E given F. So that means lung cancer given cigarette smoking. So F will be our condition. Based on some condition, what will be the outcome? So now here we say let E and F be event with probability of, always probability of F should be greater than 0 because that's the condition. This is conditional probability of E given F. So probability of E given F is always probability of E and F occurring together. Probability of E and F, which means probability of I smoke cigarette and I'll have cancer divided by probability of I smoke cigarette. Because not everybody that smokes cigarette have a lung cancer. So to find the probability of smoking cigarette and have lung cancer, it should be probability of I smoke cigarette and have lung cancer divided by probability of everybody who smoke. Probability of F will be everybody that smoke, including those who don't have no cancer. But probability of E intersect F means the two conditions. Again, intersection means the two conditions must happen. So probability of E intersect F means probability, let's say again, F means smoking cigarette, E means I have lung cancer. So this will be probability of I smoke cigarette and I have lung cancer divided probability of everybody who smoke. So let's see an example here. We have a bit string of length 4, which was generated at random so that each of the 16-bit strings of length 4 is equally likely. Now the question said, what is the probability that it contains at least 2 consecutive zeros? That's what we are looking for. It's like I'm looking for what is the probability that I'll get a lung cancer, given that its first bit is a 0. So our condition is that the first bit have to be 0. So what is the probability that that bit contains at least 2 consecutive zeros, given that the first bit is 0? So our condition is the first bit is 0, and we're looking for 2 consecutive zeros in the 16-bit string. So the solution will be, again, let E be the event that the bit string contains at least 2 consecutive zeros. So this is what we are looking for. Then F will be the condition. So the F will be the event that the first bit is a 0. Now, since we know that E intersect F, all the possible combination of 16-bit strings of length 4, these are the digits that we can get a consecutive 2 zeros. So it will be 0, 0, 0 when all of them are 0, or 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0. Otherwise, we may have 0, 1, 1, 1, or 0, 1, 0, 1, etc. But again, these are the possible, and they are 5. So which means our condition, probability of E and F together will be 5, 6. Again, 5, 6 doesn't mean E given F, but rather it's like probability of I have lung cancer and I smoke cigarette. So probability of E and F. Probability that I have 4 consecutive, I have 2 consecutive zeros in the 4 strings, and F means it starts with 0. So you can see all these values start with 0. Now, if I have 1, 0, 0, 0, it's not included because the condition said we start with 0. So that will be 5, 16. Now, to find the probability of, we have 4-bit strings. And the first, which is F, the first digit is 0. That's the condition. E should have at least 2 consecutive zeros. So that would be the probability of E intersect F. Probability, what is all the possible probability that I have a value that's the 4 digit that start with 0, and we have at least 2 or more consecutive zeros inside. And we saw that was 516. Divided by probability of F. Now, probability of F means half of them will start with 0 and half will not start with 0. So they are all 16, 8, 1 half. So when we do this calculation, we get 5, 8. Probability of F will be half of all the digits, or the strings will start with 0 and half will start with 1. So we have another example here. What is the conditional probability that a family with 2 children has 2 boys, given that they have at least 1 boy? So that's our condition now. We are looking for probability that the family have at least 2 children that have 2 boys, but at least 1 boy, given that they have at least 1 boy. Again, what is the conditional probability that a family with 2 children has 2 boys, given that they have at least 1 boy? Now here we say we are assuming that each of the possibility will be, if I have 2 children, I may have boy, 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 girl, girl, boy, girl, girl. These are the possible combination I can have. It's equally likely where B represent boy and G represent girl. I have only 2 children. So possible combination can be 2 boys or 1 boy, 1 girl, or a girl comes first before the boy, or both are girls. So if that's the case, we let E be the event that the family has 2 boys, and we let F be the event that the family has at least 1 boy. So E will be BB, then F will be BB, BG, GB. Conditions said at least 1 boy, so these 3, and event of 2 boys. So this will give us again probability of F. As we can see here, we have 3 out of 4, so 3/4. The probability of I have a boy, given boy again, is only 2 boys, 1/4. So the answer will be 1/4 divided by 3/4. Probability that again I have at least 1 boy, divided by probability of that I will have all boys. So next we move to the concept of independency. When we say independency is that at least if we have a minimum of 2 events, did one event depends on the other? A very simple example I will give. And what is the probability that when I'm going out, I will put on white shirt and green trouser? Now, if I have a condition based on my choice that anytime I put on white shirt, I will put on green trouser, then I have to count all the different colors of shirts and trousers I have, and I'll do the combination. I will come up with something, which means they are dependent. The white shirt and green trouser depend on each other. Anytime I put on the green trouser, I'll put on white shirt. Or anytime I put on white shirt, but independency means I don't care. I can randomly select white shirt and put on blue trouser, put on green trouser, put on any trouser I want. So independence means one event doesn't determine the other event. Dependence means one event determines the other event. So here we say event E and F are independent if and only if probability of E intersect F is equal to probability of E times probability of F. they are independent. E and F are independent. So the probability that you get both will multiply each probability. So here, for example, suppose E is an event that randomly generates bit strings of length 4 begins with a 1, and F is the event that this bit string contains an even number of ones. Now the question is, are E and F independent if 16-bit strings of length 4 are equally likely? Now the solution here is that there are 8-bit strings of length 4 that begins with 1. This is almost the same example we did before. And the rest of the other 8 will begin with 0. And also 8-bit strings of length 4 that contain also an even numbers of ones, which means you have 1, 1 within even numbers of 1, or 1, 1, 1, 4 ones. Since the number of bit strings of length 4 is 16, here we can say probability of E is equal to probability of F, and which will be 8 by 16, which will give us half, based on the condition of what is E and F. Now, since E intersect F, these are the possible 1, 1, 1, 1, 1, 1, 0, 0, 1, 0, 1, 0, 1, 1. We say the ones are evens. So this will be 1, 2, 3, 4 possible combination. So probability of E intersect F is equal to 4 divided by 16, which will give us again 1/4. Then probability of E intersect F is equal to 1/4 is the same as saying probability of E times probability of F, which will give us half and half. That's also 1/4. So here we are going through the concept that if two events are independent, even if it's 3 or 4, and the probability of each one, we multiply them. We don't sum it. Sum means all. That's what we said, that probability of E union F will be probability of E plus probability of F minus probability of E intersect F, because we know E can appear by itself, F can appear by itself, and they can appear both. So we had all. But probability of E intersect F means both have to appear at the same time. So E cannot appear separately, F cannot appear separately. Both of them have to appear at the same time. So it will be probability of E times probability of F. So another example, again, the same concept of two children having two boys, different ways. So assuming, as in the previous example, that each of the 4 ways a family can have 2 children is either two boys or 2 girls, or boy comes first before girl, or girl comes before boy, is equally likely. Now, are there event E that a family with 2 children has 2 boys, and F that a family with 2 children has at least 1 boy independent? So that's the question. We want to know if a family have 2 boys or at least 1 boy, which is boy and girl, are they independent? So this is our solution. Because E equal to 2 boys, PP, probability of getting E, when we look at the combination, we have 4, it's only 1. So probability of getting E will be 1/4. Or BB, GG, BG, GB, total sample space is 4, and BB are purely 1, so 1/4. We saw that previously that the probability of F is 3/4, and probability of E intersect F, both occurring, is 1/4, which is BB. The event E and F are not independent, since probability of E times probability of F will give me 360. We also have the pairwise and mutual independency. The concept here says that if we have events, E1, E2 up to En, it can be any number of events, and we say they are pairwise independent. If and only if probability of I intercept probability of J equal to probability of I times probability of EJ for all the pairs I and J. The concept here is again independency. But we have a pairwise separately, a list of I's and a list of J's, and we combine. So the events are mutually independent if probability of I 1 intercept probability of I 2 intercept probability all the way to EIM can be any amount equal to probability of EI1, probability EI2, all the way to EIM. Whenever J start from 1 to M are integers with the following. The total I1 should be less than or equal to 1, also less than 2, all the way to the number is M. And M should be greater than or equal to 2. What we mean by M is not the probability value, but M is the number of items. So let's say J start from 1, 2, all the way to M. So we should have at least 2 items. So that will take us to the next topic, which will be our last topic. What is a Bernoulli Trials? So suppose an experiment can have only 2 possible outcomes. Example, flipping of a coin or random generation of a bit. Each performance of the experiment is called Bernoulli trial. That's the whole concept. This will lead us to binomial distribution, which we are not going to cover in these lectures, but that will be the next lecture. Bernoulli trial, what it means is that when we do any experiment and the outcome is 2, so suppose an experiment can have only 2 possible outcomes. Example is flipping a coin, head or tail, or random generation of a bit. A bit is 0 or 1. Or experiment of a cancer studies. Either the patient have a cancer or he doesn't have a cancer. Or in binomial distribution, we can have a problem that what is the probability that a plane will be late to its destination. This would be a Bernoulli because a plane can either be late or arrive in time. So the only possible outcome is 2. Now, one outcome will be called a success. So in terms of the plane, if the plane arrive in time, that's successful, probability of success. Otherwise, if it's late, then failure. In terms of cancer, if it's positive cancer, that's maybe failure. And if it's not cancer, then maybe that's success. So if P is the probability of success, then Q should be the probability of failure. And since we know that the probability, again, this experiment have only 2 outcomes. So if one outcome is 0.4, the other outcome should be what? 0.6. So the sum of P plus Q always will give us 1, the total. So many problems involving determine the probability of case success when an experiment consists of mutually independent Bernoulli trials. And we will see many of these type of problems in binomial distribution. So we know tossing a coin, the only possible outcome is 2, so it's a concept of Bernoulli trials. So a coin is biased so that the probability of heads is 2/3. What is the probability that exactly 4s occurs when the coin is flipped 7 times? Now, this time the coin is going to be flipping 7 times. And when we flip the coin 7 times, always we have a possible of what? 2 outcomes. So here we say that there are 2 to the power 7 possible outcome. 7 times, always 2 outcomes, so 2 to the power 7, which will give us 128 possible outcome. Now, the number of ways we saw 4 of the 7 flips can be heads will be combination of 7, 4. As the question said, what is the probability that exactly 4s occur when the coin is flipped 7 times? So the coin is flipped 7 times and the 4 head occurs. So it's combination of 7, 4. So the probability of each of these outcome is 2/3 to the power 4 and 1/3 to the power 3, since it's 4, since the 7 flips are independent. Hence, the probability that exactly 4s occur is 674, 2/3 to the power 4, 1/3 to the power 3. Now, if you do these calculations, you get 560 divided by 21 by 87. So we have probability of K success in an independent Bernoulli trials. So the same concept as we said earlier. This takes us to binomial distribution again. So what is the probability of exactly K success in an independent Bernoulli trials? With probability of success P and probability of failure Q. We know Q will be 1 minus P, is given as this formula here. This is the formula again for binomial distribution problems. It will be a combination of n. N will be the total number of tries. K will be the number of success to the power P, probability of success. K is the number of success, then P to the power K, Q to the power N minus K. Q is the probability of failure. Anytime, most of the time, they will give us probability of success. So to find Q, it will be 1 minus P. Now, let's try one example here. First of all, we go through this definition. Random variable. So what is a random variable? A random variable is a function from the sample space of an experiment to the set of real numbers. So in our question, random variable can be how many times we have a plane that is late. The number probability of, probability of, let's say the probability of 10 planes being late is 0.4 or something. But again, the best way to do this is we go straight to an example. First, let's see an example of a random variables. So here they said, suppose that a coin is flipped 3 times. So let S at T be the random variable that equals the number of heads that appear when T is the outcome. Then S at T takes on the following values. S at 3H equal to 3 because 8. And here we don't have any H, so it's 0. Now, H appeared twice here, H appeared twice here, H appeared, so it's 2. H appeared once. This is again based on the question. The coins flipped 3 times. First, all the 3 times was H, so 3. All the 3 times were T, so there's no any H. H comes first and second, then T. H comes first, then T, then H again, stay 2. T, then H, so total 2, and the same concept here. So now each of the 8 possible outcomes have a probability of 1/8. So the distribution of S at T is P at S equal to 3, it's 1/8. P at S equal to 2 will be 3/8, and P at S equal to 1, 3/8, and P at S equal to 0 is 1/8. S with no, this is TTT, no X again, 0. So we are going to end somewhere here in our exam. Again, those 2 sections are just some few examples. We're going to discuss that one in our next lectures, which again goes with the binomial distributions. So again, wish everybody the best and thank you.